Scholastic greetings to each and every one of us in class today. On behalf of Erudite Tutors, I want to welcome you all to CIT392, Computer Laboratory 2. And this course is targeted at 300 level second semester students of Computer Science and Information Technology departments, as well as Computer Science in Education, 300 level first semester. Once again, you're all welcome to class. And my name is John Osage. For those who know me well, call me Dr. John. We'll quickly go into the course. I'll be your instructor for this course all the way throughout the semester, and I want to wish you success in this course. Computer Laboratory 2. As its name sounds, computer laboratory, what do you expect of a computer lab? Of course, this course is sequel to Computer Laboratory 1, where, of course, you would have come across the introductory part of Computer Laboratory and the things you go on to expect and advance. And in this course, Computer Laboratory 2, we'll be going a little further than just the preambles. We should be expecting a lot more of programming now. Programming. But before we go into the programming proper, let's begin to see the introductory part of the programming. What is programming? What to expect of this course generally? And we will run through with all of the explanations necessary for us to have a scholastic performance this semester. In Module 1, we're looking at computer laboratory exercise on programming languages. Module 1. Laboratory exercises on programming languages. As you can see there, introduction to programming, programming in C language, programming in C++, programming in Java. Those are the units we have in Module 1. So let's go straight into the Module 1. I'd like to begin by saying there are problems almost everywhere. In our daily lives, there are problems. And the whole idea of programming is to solve problems. The whole essence of programming, in whatever form, simple as it may be, complex as it may be, the whole idea is to solve problems. So when we say problems, real world situations, there are problems everywhere, problems every day. And they are all attempted to be solved one way or the other. Everybody's solving one problem, even by mere thinking or cracking the brains or just profiling advices or whatever way, we are all solving problems. We are all solving problems. Now, every problem that poses itself in front of anyone, the first step at solving a problem is to conceive a solution. To conceive a solution. And whereby a solution is conceived, then we begin to draft some actionable steps. The solution that is conceived based on the problem that poses itself, then we begin to draft some actionable steps that can be taken, actionable, practical steps. They are all developed in line with those conceived solutions now. The idea that is conceived as a solution is now put into steps. And eventually, those steps, they are now transformed into the program instructions. Let's not forget that the actionable steps developed towards solving any problem is known as the algorithm. We've said that before. We have learned that in previous courses. Algorithm, the step-by-step approach to solving any problem. It usually is expressed in our regular English. So, step 1, cross the road. Step 2, take a bus. Step 3. And then all of that is geared towards solving the problem of getting to the office on a Monday morning. So the actionable steps is the algorithm. Now, putting those actionable steps into a comprehensible language for the computer to interpret and execute is what programming is about. Communicating with the computer such that it can understand those actionable steps that has been drafted. And of course, the kind of problems we give the computer to solve are not the type of crossing the road to the office and all of that. But you can see problems like sorting, ascending order, arranging in ascending order, sorting out, counting the number of responses with a yes. Those little mathematical problems, they are the types given to a computer. So the person who has the problem to solve can now begin to put it, okay, first of all, I will count. Then next of all, I will remove this. Then again, I will take that out. And then I will sum them all together. Then I will find the average. All those are actionable steps. And how are they now given to the computer to interpret in its own understandable language and execute? That's exactly the whole idea of programming. Now, in this course, we will be identifying problems. We will be creating a mental picture of solutions. It's all part of the programming skills. And then listing out the actionable steps from the mental picture of the solution we've created. And don't forget, problems comes in different shapes and sizes. Solutions also comes in varieties. So we can have for one problem 3 or 4 solutions. We always try to find the optimum solution, the best solution that will not take us through a lot of problems, that will not give birth to other problems, that will be the minimum to execute, the shortest to solve the problem. So actionable steps again, the mental picture again, all of those have a lot of work to bring out the best solution before now putting in them into actionable steps. So moving on, we will be listing out the actionable steps, most optimum actionable steps from whatever mental picture we have conceived, and then finally converting those steps into a list of comprehensible instructions for the computer to execute. And we'll be looking into a lot of things like the rudiments of a programming language, basic construct, a lot of things. But let's begin again from our notes here by introduction. In any language, there are some fundamentals, very essential. Fundamentals you need to know before you can even write the most basic elementary programs. Now, fundamentals were what I was going to talk about. Rudiments of a programming language, basic constructs. Basic constructs include the syntax and the semantics. The syntax talks about the format, how the constructs are put together, what should come before what should not be in the construct. Should a comma be here? Should a full stop be there? All those little grammatical constructs. They are the things we should know before venturing into any programming language. We also have the character sets. What are the elements that are recognized in every language? Like even in our typical English language, there are some words that are not allowed. They are known as vulgar words, vernacular, and all of those. So in different languages, there are certain words, characters that are allowed. There are some others that are not allowed. So the acceptable character set in each language must be well known. We have strings, we have numeric, we have floating points. All those are data types. We also have variables and functions, declaration, how to call a function, how to declare variables and functions. We also have basic operations like addition, subtraction, sorting, find, replace. All those are basic operations. The input-output, the logical operations, arithmetic operations. All those are just the basic rudimentary elements that one must come to terms with before settling in on any programming language. And then having known all of this, maybe not in entirety, but at least for the beginner's idea of all of this, we can begin to play around with problems and then conceiving a solution, best practice solution, and then the actionable steps, and then the programming language constructs. Okay, so programming, basically, the origin of programming started with machine language. Machine. Of course, it is a computer we are communicating with. So how else can we communicate with a computer if not the language it understands? And that is the machine language. What is a machine language? language in zeros and ones, binary language. That's just what the computer understands. So anything you're giving to it must be well simplified for it to recognize. Zero here means no, not, false, negative. And then one here means yes, true, on, positive. So whoever is going to be instructing that computer must be able to bring out the solution, the actionable steps, in such a language as simple as the zeros and ones for the computer to understand and then execute. So it all started with machine language, and it began to evolve. The programmers of old, they were usually very good professionals, because it takes a lot of effort to do the coding in zeros and ones. A lot of professionalism go into it. And at those times, problems were very simple kind of problems, like just counting, like just regular imputing. Impute these responses. Say, for instance, a questionnaire goes out and some persons respond to the questionnaire, yes, no, I don't know, and the likes. So first of all, how does this input get into the computer? It takes a lot of programming. And then when the responses have been imputed into the computer, they have to be sorted. How many came back with a yes? How many came back with a no? How many were like, I don't know? So all those sortings were the simple operations that were carried out in days of old, but it took professionals to interpret the instructions that will perform those solutions, that will do the sorting, that will do the counting. It took professionals to give the computer the right instructions to carry out those tasks. And those were days when, if you were a programmer, you are a big deal, a guru. But then what were they doing then? Simple tasks. Very simple tasks. Compared to today, when anybody in Yoruba class can just pick up Microsoft Excel and begin to enter yes, no, so, and all of that. It's so, imputing is so easy now that it doesn't really take a professional. So you can see the difference between then and now. In any case, programming started far back as then with computer professionals just solving simple tasks. And then it's really pushed a lot of people backward from using the computer, because not everybody was a professional, so to speak. Not everybody was interested in knowing the rudiments and how to convert those actionable steps into computer machine language. But gradually, programmers began to think, and then ideas began to come about, evolution. There was a lot of advancements and improvements, such that languages were beginning to evolve that were like intermediary between the computer and the programmer. The computer and the programmer, they were like middlemen. Again, in any language, there are some fundamental things you need to know. I'm reading from the introduction part now. Before you can write even the most elementary programs, this unit introduces this such fundamentals: the basic program construction, the variables, the inputs. We talked about this. Also, it touches on a variety of other language features, including comments, arithmetic operators, the increment operators, data conversion, and library functions. Okay, we talked about all of this as the introductory part. So now, the programming now, under the headline 3.0, programming. The digital computer is a useful tool for solving great variety of problems. Now, what is a digital computer then? It's similar to what we have today, computers, but not like the analog. Analog is where you have the button inputs, those knob television of old, where you have to switch between knobs. But in digital computer, you have buttons, you have touch screens, you have digits showing around it. All our touch screen, smartphones, everything today are digital computers. And so a solution to a problem is called an algorithm. Yes, we said so. And it describes a sequence of steps to be performed for the problem to be solved. Now, problems, sort the list of names, algorithm, call the given lists, okay? Now, we all of this are just paraphrasing on the introductory part. I'm really interested in us understanding the evolution of programming language. As we went on with programming and programmers of old, they began to think there were bigger problems confronting them, and they needed to solve these bigger problems. So how would it be that a bigger problem needing more instructions, greater professionalism can be done easier and can be done by almost anybody who is not even a professional? And so the middlemen came in. The middlemen happened to be platforms, software platforms that will stand between the programmer in his own natural English language and the computer in its own machine language. Those middlemen, the software platforms, were like translators. They were like interpreters. They were like those things that can understand this end and understand that end and can be the middleman. Take, for instance, a Frenchman and an Englishman. An Englishman speaks his English and a Frenchman speaks his French. And then there is a man in the middle who understands the English and understands the French. He takes from the Englishman and he gets the point that the Englishman is trying to pass across. And then he interprets it to the Frenchman in his own French language. And the Frenchman gets the message and sends a feedback. I say, okay, tell the Englishman this in his own French language. And then the middleman gets the message from the Frenchman and then sends it to the Englishman in English language. So this became the order of the day gradually, and we began to have programming languages. First, there was machine language, the zeros and ones, computer language. And so programming languages evolved. First level of it was the assembly language. The assembly language. If we read the second paragraph there in item 3.0, an algorithm is expressed in abstract terms. To be intelligible to a computer, it needs to be expressed in a language understood by it, the computer. The only language really understood by a computer is its own machine language. Whether you go from here to anywhere in the world, that is the only language the machine understands. Machine languages, zeros and ones. A program expressed in machine languages are said to be executable. Yes, executable. They are in raw form. They are direct instructions that the machine can just pick and execute. It does not need any form of translation. It does not need any form of anything else to be done on it. Just directly to it in machine language, it executes. Now, a program written in any other language needs to first be translated to the machine language before it is executed. And that's where the middlemen come in. Any other language at all. But then it was helpful in the sense that human beings can now communicate with computers, not in the exact machine language, but in a semi-relative language closer to the human being's language. And then at least away from the machine language. At least it was getting easier to communicate. Just give certain false instructions, mnemonics, some things that look closer to human language. And then the platform, the intermediary, the translator in the middle does the translation and gives the computer what it expects to understand. So we have the assembly language was the very first class of programming languages that came up, the assembly language. And then the tool for conversion of the assembly language is the assembler, the translator that does the conversion from whatever you input into the assembly language, whatever you input into the assembler is assembled into machine language. So you cannot just go from an assembly language straight to the machine language, no. So understand there that assembly language is one of the very first generation of programming languages. The very first generation of programming languages. And then gradually, there were other programming languages that became like low-level languages, then high-level languages. The evolution was such that the programming languages were becoming closer to human language, they were gradually looking easier for humans to understand. In fact, in our regular English, we can just type if, yes, then, not, else. Regular English, and you're already given instructions from what you are able to conceive in your head. You're already given instructions, and then the translator there now does the conversion into the machine language. No matter from what level you're bringing it from, it just translates, converts into machine language. And then the machine understands it in its own machine language and then it executes it. And so further down the paragraph, we see high-level languages like C++ provides a much more convenient notation for implementing algorithms. They liberate programmers from having to think in a very low-level terms. Look at that. They have to, the high-level languages ease the programmers from having to do a lot of thinking in low-level terms, in closer to machine languages, rather in their own natural English language or high-level languages. Programmers just think. And so programmers can now focus on sophisticated problems, bring out extensive solutions, provided the language to convert it to is something closer to the language we speak. So they can express high-level, sophisticated solutions and let the translator do the conversion. Now, we'll go on to explain these levels of programmings. We have the assemblers, like I mentioned. We also have the interpreters, and we have the compilers. The assemblers, the interpreters, and the compiler. What makes an assembler an assembler? It is the assembly language it is written in. And it takes in an assembly language and does the translation into machine language. And now, what is an interpreter? An interpreter there takes instructions from the programmer in its own language, low-level language most likely, more low-level language. The interpreter, it's also a translator. Let's understand this. They are all translators. They are all translators. But in the class of translators, there are assemblers, there are interpreters, and there are compilers. The assemblers are in the class of their own, assembly language. Then the interpreters, they are more of the low-level language translators. Low-level language translators. Then the compilers are the high-level language translators. The high-level language translators. One other thing that stands out very distinctively between the interpreter and the compiler is that the interpreter takes the instructions and executes them one line at a time. So the programmer has done his job, putting all the instructions and then sending them into an interpreter. Now the interpreter takes it one line of instruction first. He does the translation, sends it to the machine language or to the machine in its own language. The machine executes that and then waits for the next set of instructions. The interpreter picks the next line of instructions and then sends it after translating, one after the other, like that. Now, the disadvantage to this is that it could take a long time before the execution is completed. Because back and forth, taking one instruction per time, does the translation and sends the corresponding translation to the machine, it takes a longer time. So for a very simple task, the interpreter will take a long time. But for the compilers, how they do theirs is that they take all the instructions given to it by the programmer, they do all the translation once, convert everything to the machine language in one bulk. All the lines of codes are translated once, and then everything generated in machine language is sent to the machine at once. In so doing, it is faster. It is quicker to get tasks performed using compilers. And don't forget, these are high-level language translators. So, of course, everybody's happy with that because the language is closer to human language, and the compilers, they translate faster. So, the new age programming language we have today, we are all working with compilers. Here and there, most of the languages you see today, high-level languages, C++, C#, Java, they are all high-level languages, and they are all working on compilers. And it makes programming so easy that not even a professional only can pick on. I mean, today we now see coding classes for 6-year-olds, 7-year-olds, 8-year-olds. That is how easy it has become. And I tell you what, it gets easier and easier. So now we understand some of the foundational history of programming language and how it has evolved to date. Let's look into programs. Programs. What are programs? I mean, what is that thing that is written? The whole programming, the whole action called programming. What is that thing we are doing? We are writing programs. What is a program? A program can be one of two things. First of all, it is that lines of instruction that is written by the programmer. Those lines of codes that you put together in whatever language you are writing it now. Be it high level, be it low level, maybe assembly, even if you like to do it in machine language. In whatever language the programmer is writing, whatever he has written down as a set of instructions from the steps he has conceived, that's a program. That's a program. But what type of a program is it? It's a source code. It is a program, yes, but it is called a source code. The code from which the instructions is originally coded is the source of the instructions. Mind you, this may not be directly what the computer will understand. It's everything else but the machine code. So it can be in assembly, it can be in interpreter, it can be in the compiler. I mean, it can be in the assembly language, the low-level language, or the high-level language. So any lines of instructions written in assembly language, low-level language, high-level language, they are all the source codes. And they are all programs. Yes. Now, what else do we refer to as a program? What else can we call a program? It is that translation that has been done from the set of instructions written by the programmer. And this is taking what has been written in either assembly language or the low-level language or the high-level language, and then having translated it to the machine language. That now is also called the program. But what kind of program is it? The executable code. The executable. Yes. The executable code, or the executable file. Just the executables, whichever one you just note the difference. The source is the origin set of instructions. The executable are like the destination language, the machine language set of instructions translated from the source code. But both of them are still called programs. So as we go higher in this course, as we become more profound with it, we will definitely want to be clear. Anytime we hear the word program, this program, you want to know, is it a source code? Is it an executable? You want to be sure you have it distinctively. Now, we're looking at, let's read this line there. Say we'll throw a little more light on what we've been talking. A program can be defined as either a set of written instructions created by the programmer or an executable piece of software that all now separates it. Written instruction by the programmer or an executable piece of software. Now, source code can be turned into an executable program in two ways. Interpreter translates the source code into computer instructions, definitely in machine language, and then the computer acts on those instructions immediately. Alternatively, so we see how the interpreter does its work there. The interpreter translates the source codes into computer instructions, and the computer acts on the instructions immediately. So one line at a time. One line at a time is taken from the memory where the source code is resident, translated, given to the computer acts on it and waits for the next set of instructions, and then the interpreter goes again, take the next line of instructions, and so on. Alternatively, the compilers translate the source code into a program which you can run at a later time. So the compiler just takes the whole chunk of instructions, translates everything, and then it stores the set of executable files, stores it. So if you want it to run at that moment, you just execute and it runs. And you can also save that executable file for further use, for future reference. You want to run that program again later, you just save the executable, and then the computer will keep it somewhere, and next time when you come around, you just click on the executable file and then it runs. And the computer observes the whole instructions like it's coming afresh. So it's a lot easier with compilers, and life just gets better with high-level language. I will see here C++ is a compiled language. Now, solving problems. Let's look at this whole idea of solving problems. We have paraphrased on this already with how problems evolved, emerged. It became a problem for professionals having to think through high-level problems, sophisticated problems, and the whole machine language task, the burden of translating the solutions into machine language. So that gave birth to the evolution of programming languages. So let's read through the paragraph and throw more light on it. The problems programmers are asked to solve has been changing. Take it or leave it. Problems have been changing. Today we have problems as sophisticated as banking enterprise applications, banking softwares. Those were not there some 20 years ago. They were not there. So problems have really been changing. I read further. 20 years ago, programs were created to manage large amounts of raw data. Raw data. The people writing the codes and the people using the programs were all computer professionals. Today, computers are in use by far more people, and most know very little about how computer programs work. Not everybody is a professional like this. Everybody just pick up a computer and just wants to get work done with it and move on. Doesn't want to worry about the technical side of how the computer works. Today, compilers are tools used by people, or computers are tools used by people who are more interested in solving their business problems rather than struggling with how the computer works. Ironically, to become easier to use for the new audience, programs have become far more sophisticated. So languages have to come in to help with a lot of the professionalism that is required. Gone are the days when users typed cryptic commands at esoteric prompts only to see a stream of raw data. That paints a picture of you just want to retrieve line of code, just line of record, database query. Just want to draw one line of instruction and then you have to write a whole bunch of codes. It's crazy. Gone are those days. Gone are really those days. In any case, today's programs are sophisticated. They use user-friendly interfaces involving multiple windows, menus, dialogue boxes, and a myriad of metaphors which we have become familiar with. The programs written to support this new approach are far more complex than those written only 10 years ago. The platforms for which we now interact are far more complex. The problems we are even solving are far more complex than what we even had some 5 years ago. So evolution has taken place, problems have emerged and evolved, some greater tasks are being performed, People are solving crazy problems. Thank God for programming language and the evolution and the withdrawal of all the professionalism, now focusing on the sophistication of problems. With the development of the web, computers have entered a new era of market penetration. More people are using computers than ever before, and their expectations are very high. In the last few years, programs have become larger and more complex, and the need for object-oriented programming techniques to manage the complexity has become manifest. Wow, object-oriented. That's another interesting one there. And we'll get to it as we go on. As programming requirements have changed, both languages and the techniques used for writing programs have also evolved. Very interesting stuff there. Very, very interesting. It's worthy to note that problems that are solved years ago in the lines of codes that were used to solve them, if they are put up now, you'll be wondering what happened. Some huge 10,000 lines of codes just to count through a file of 100 records and some little assignments. If you translate it into what obtains now, 2, 3, 4 lines will replace 10,000 lines of codes of old. So the evolution is really, really dramatic. It has really made a lot of jobs easier. Tasks have now evolved. More huge problems are coming in. Yes, we still have lines of codes that are 10,000, but you can trust that the problems they are solving are much more sophisticated. And so the whole idea of programming is just solving problems. And I'm sure at this level that we are studying this course, we want to condition our minds that we will use this idea of programming and as required, solve problems. And even as we are solving problems now, we challenge ourselves that as I am learning of it today, I'm solving a particular problem with it today. In 5 years from now, I should be thinking outside the box on how to solve a bigger problem with this same programming language or whatever advancement. Otherwise, programming will still have been what it was. So it's a challenge, it's a call on everyone who is studying programming to keep looking at how improvements can be done. And I want to believe somebody from this class will definitely be on the list of names that will come up with new ideas, groundbreaking evolutions, and it will be worthy of note. Yes, moving on to procedural, structured, and object-oriented programming. Interesting stuff here. Procedural, structured, and object-oriented programming. These are forms of writing codes. And believe you me, there has been evolution between these three: procedural, structured, and then the object-oriented programming. There has been evolution. There has been the use of one, thinking that was the best, and then there was the problems that came up with the use of it. There were the limitations that were observed, and then there was the evolution to another level. Yes, and that felt like it was better than the previous. And then few years down the line, problems began to evolve again, and there was a need to go higher, and then object-oriented came in again. And as of today, yes, object-oriented is what's in vogue. In the next 5-10 years from now, the GMA shifts, and that's why it's a wake-up call again for everyone who is studying this course to keep looking to see what can be done better. Let's read through 3.2, procedural, structured, and object-oriented programming. Until recently, programs were thought of as a series of procedures that acted upon data. Listen to that. Series of procedures. The first idea, the origin, how programming was first perceived was a bunch of instruction, bunch of codes that solves a particular problem, and that lines of code that represents the solution to a problem will act on a given data. Procedural. Okay, procedural can be, yes, count through a number of files. Just that. Count through a number of files. So it is left for me now, okay, what are the actionable steps? I have to take the number of files. I have to be able to count them and then summing up their numbers. Okay, 1, I add it up to the one I've counted. Take another file, this is 2, I add it up. Take another file, 3, I add it up, and so on. Adding up to the previous total. That's counting now. So a procedural program just puts up a number of lines of instructions that does the counting, and then it waits for an outside data to act upon. The outside data is now the number of files. And the files themselves, you need to count. Maybe in a file, you need to go and locate the index number. And so the index number is what we're counting. So each file that comes in, index number 1, index number 2, index number, and so on. So there's something from the outside that comes into that set of instructions, like a something enclosed in itself. Procedural, it solves a given problem. Procedural, and then it waits for the data to act upon. A procedure or a function, I read further now, is a set of specific instructions executed one after the other. Now, the data was quite separate from the procedure. Did you see that? The data always stands separate. The procedure is always like it's self-contained, self-sufficient on its own. So it will leave room for the imputing of the data, which always comes from the outside. And when it receives the data, it acts on it and then gives a feedback. Okay, that looked like, as at then, it was beautiful, it was lovely, it was the best form, the best methodology of programming. And then life was good as of then. But then, and the trick in programming was to keep the track of which functions called which other functions. So there were procedures that could refer to other procedures. Okay, while I am doing the sorting, I also need to do the counting. Sorting is one procedure on its own. Counting is another procedure. What about averaging? Inside this set of files that are supposed to be the input now, I'm sorting, I'm counting. I also need to do the average of maybe some numbers that are in the files. So while I'm locating the index number and counting, I'm also locating a particular field that has yes or no and yes or no, and I'm counting them. I'm putting the yeses separate and the no's separate. And then while I'm also doing that, I need to refer to another procedure that sums up another set of numbers in each of the records, in each of them. So the numbers are now located and then they are added up. Previous sum added up onto the total. So one procedure, one function could call a second and a third and a fourth while it is executing its own initial operation. And I need all those responses. So it looks like it was good. One procedure kept track of, okay, this one starts its own operation, but it is not finished. It calls another function. Okay, while this one is still running, another function is running, and then I'm trying to get the answer to that one to come back to this first one. And while the second one is running, it calls a third one to quickly do something and get back to the second one while the second one continues. And when it finishes, it comes back to it. They have to keep track of which procedure refers to or calls another procedure while it is still in operation. And so as not to lose track of this procedure did not finish, went to another one, and it never came back. No. Procedures are so modular that, yes, they can keep track. Now, to make sense of this potentially confusing situation, structured programming was created. Now, the whole keeping track was a problem because you could have one procedure refer to like 7, 8, 9, 10 other procedures, and it becomes so clumsy, you could become so lost. As you are in the first procedure, while it is still operating and working on the records, it calls the second procedure. Okay, we quickly rush to the second. And while it is calling the second procedure, the first procedure is like temporarily put on hold. It calls the second procedure to quickly run a particular quick operation and get back. And while it is running that operation, it comes back to the first one, yes, very good. And then it continues on that first one again. Somewhere along the line for that first procedure, it calls the second one again. Okay, let's quickly do the second one the second time and go back to the first. But this second time, it calls a third procedure. Okay, we go on to the third procedure. The third one can call a fourth, fifth, and sixth at the same time. Wow. And then you have to be sure that each of them are running. The fourth one could return to the third one. The fifth calls the second, the next one. In fact, they are so interchangeable that the seventh procedure that is called can call back the very first procedure that the whole call started from. It's so intertwined, it can be really confusing. So, to make sense of this potentially confusing situation, structured programming was created. Now, the principle behind structured programming is as simple as the idea of divide and conquer. Okay, we see that in politics, we see that in game of numbers. Yes, politics, yes. Divide and conquer. How does this work? A computer program can be thought of as consisting a set of tasks. Any task that is too complex to be described simply would be broken down into a set of smaller component tasks. An example is computing the average salary of every employee of a company, and is rather a complex task. You can, however, break it down into the following subtasks. Now, do you see the idea of, instead of compounding modules, structures, just break them down into smaller bits from the whole big one to smaller bits. Now, let's not forget, in the procedural, each of those procedures are not like mother and daughter. They are not like one is superior to the other. Every one of the procedures are like on the same level, hierarchically. They are like equal. So they are just traversing each other. But in the structure, there's always the mother structured program, which now calls a sub, and then a smaller one, and then a smaller one. They all have smaller chunks of tasks inside the bigger one. So it makes it easy to manage when you have called the major program, and inside that major program, it assigns each of the tasks to a smaller chunk of instructions. All of them will still have to return to the bigger program. So it's like a hierarchy of programs, the bigger one, then the smaller one. So let's see what it says here. You can, however, break it down to the following subtasks, talking about computing the salary of every employee. The first task there is to find out what each person earns. So that could be a smaller task. And then another one here is count how many people you have, employees, how many employees that are there. And then the third task could be total all the salaries. You see that? And then the fourth task could be divide the total by the number of people that you have. And that's the average. So sharing each of these small tasks, chunk of, and they don't get to conflict. One will completely execute. Whatever it brings as output is what will go as input to the next one. And then the second one will bring out its own output and give it to the third. And the third will bring out its output, give it to the last. And when the last is done, they submit it back to the mother structured program, the mother of their programs, which now gives the outputs. Like, okay, I have taken this set of instructions in. I was asked to find the average. And so I have my children. So you take this first one, quickly get it done, give it to the second one, you get your job done. And so the mother now brings out the outputs to the programmer eventually. Now, totaling the salaries can be broken down further into the following steps. Don't forget that totaling the salaries there is the third set of instruction in the first four subtasks. Now, breaking that number 3 instruction now, get each employee record, access the salary, add the salary to the running total, get the next employee record. See how that again is broken down? And each of these do not conflict. One has to finish before moving to the other. They don't conflict. And again, in turn, obtaining the employee record could be broken down into the following. 1, open the file of the employees. 2, go to the correct record. And then 3, read the data from the disk. So each of these tasks subdivided independently, they carry out themselves, get out their outputs, transfer to the next one. They are working independent of themselves, and then the whole overall goal is achieved without much of conflict or confusion, or is such that if there is a problem at any point, it can easily be traced and no data is lost at any point. No, if anything goes wrong, it's easy to tell this came from here. Unless if it was an error in the calculation, the initially programmed calculation, or maybe the data itself that was entered is an error. But if anything jams somewhere and does not go through, it can be traced. So structured programming happened to be a solution to the problem of procedural programming. But then this is not to say that structured programming didn't have its own challenges. Let's read further. Structured programming remains an enormously successful approach for dealing with complex problems. You see that? But by the late 1980s, however, some of the deficiencies of structured programming had become too clear. First, the natural desire to think of data, that is the employee records, for example, and what you can do with the data. So now, the idea of data to be independent instead of, writing chunks of codes all the time, and then data standing independently. It's always, whenever there is a new problem, a new solution, you have to go and write a new set of instructions. The data is always standing on its own. But some level of thinking began to emerge, a paradigm, a shifting in the thinking, like, what if instead of having structured programming, why not concentrate the programming around the data? And what can be done? Let the data be the focus. Let the data be the attention, the center of it, rather than the procedures and the structures and no. So the object-oriented began to think towards data, give attention to data, manipulation of data. So we say here, first, a natural desire to think of data as the employee records, for example, and what you can do with data. You can sort, you can edit, and so on, as a single idea. See that? Now, I'm reading from here now. Procedural programming worked against these separate data structures and functions that manipulated the data. Secondly, programmers found themselves constantly reinventing new solutions to old problems. That became a problem. So every time the same employee record, you have to go and write, okay, now this time around, we're no longer doing average. We want to do one other thing. You have to go and write a new set of instructions. And the same data. Okay, what again? This same employee records, we want to find the highest earner or the highest loan applicant or whatever new set of problems is always a new set of codes. And it became tiring. Like, are we ever going to stop writing new set of codes? So this is often called reinventing the wheel. Most times the new set of codes are not far from what has been written. But it's like always changing, reinventing, always putting up new things from, it's so tiring. Which is the opposite of reusability. The idea behind reusability builds components that have known properties and then be able to plug them into your program as you need them. This is modeled after the hardware world. When an engineer needs a new transistor, she usually does not invent a new one. She just goes to the big bin of transistors, find one that works the way she needs it, and perhaps modifies it. No similar option existed for a software engineer. So we're talking about, instead of always making new, reinventing the wheel, one of us focus on the data. focus on the data and then make a whole set of things that you can do with the data. A whole set of operations that can be performed. Let the operations now vary, but let the data be the attention. And so, object-oriented programming attempts to respond to these needs, providing techniques for managing enormous complexity, achieving reuse of software components. Reuse. So we didn't have to write new set of software, data is the only thing that could be changing. Data is the only thing. So now, today, one typical example of this object-oriented programming is when you see Microsoft Excel can do sorting, find, replace, copy, paste. Those are operations, different operations that can be performed on whatever data you put. The data now is the number or the letter or whatever you input. So data becomes the focus. So with a whole number of data, I can do a whole number of operations. So they began to just write different operations. Okay, sorting, yes. And sorting is written only once. Only once, sorting. When you write that sorting, so you can reuse sorting 1,000,000 times for different data. So no longer the days when, okay, this same employee record, we want to calculate something else. And then we have to go and start writing that something else for the same, a different set of employee record, we want to calculate. No, it doesn't. So now the set of operations that can be performed are written just once, but the data can now begin to be changed. So we can bring in 1,000,000 data. That is where the data now has the attention. 1,000,000 different data, but the same operation. Object-oriented programming. It responds to these needs by providing techniques for managing enormous complexity, achieving reuse of software components, and coupling data with the task that manipulate the data. The essence of object-oriented programming is to treat data and the procedures that are acted upon the data as a single object, a self-contained entity with an identity and certain characteristics of its own. Beautiful. Treating data as an object, object-oriented programming. Treating data as if it is an object. So what can we do with this object? You can pick up an object now, a phone. I can wash the phone, I can spray the phone, I can apply powder on the phone. Those are different procedures, different programs, but the data is still that phone. And then if I now decide to change that phone as my object, I put another phone, I will still bring in those same operations. Wash the phone, spray the phone, apply powder, whatever. I will still bring in, I won't have to start writing new set of programs for a different data. So the data has the attention now. It's like an object. What can I do on this object? 1,000,000 other things I can do on this object that if I so decide to change this object, I can still do those 1,000,000 other things on any object. That's the whole idea of object-oriented programming. The data has the attention and the data can be changed. So the operations began to multiply. Sorting, adding, finding, they began to multiply, and then we saw icons, the birth of user interface, the birth of graphics, icons, drop downs, all those things were now the operations. And the objects are the data. Any number you enter, any letter, anything you enter remains the data. So that's all changed the idea of programming. No longer were we writing different programs. Now, once you just build a Microsoft Windows or Office or Microsoft Excel, it's now up to you. Whatever you want to bring in as your data. If you want to copy, you copy. If you want to paste, you paste. If you want to bold, italics, underline, all those are now small chunks of operations that are written. So any data at all, you can perform those operations on them. And so this whole idea has brought us far to understand programming and the history so far, how it has evolved, and the laboratory exercise on how thinking has been done progressively at solving problems in the best possible ways. And I tell you what, where we are presently with solving problems is the best for now. It's a wake-up call on everyone who is studying this course, present generation, future generations, to look for the best possible ways and keep the evolution going on. And so conclusively, I'm reading this part now. Conclusively, a digital computer is a useful tool for solving a great variety of problems. A computer can do anything you tell it to do, but it does exactly what it's told. Nothing more, nothing less. And something is embedded in that statement. If you have a preconceived solution in your head and you have not properly translated it for the computer to execute, it will not assume the solution in your head. No. It does exactly what it is told to do. So if that preconceived solution is there in your head and you have given it some lines of instructions but not properly transmitted the solution, it will go ahead and execute, but it won't execute exactly what you have conceived. And so that's where it comes in with debugging, going into the lines of code to correct any errors, something that does not speak to the solution you have preconceived. We'll get to all of that as we go on in this course. Moving on, the conclusion line. Computers understand a language variously known as the computer language or machine language. It is possible, yes, but extremely difficult for humans to speak and communicate with the computer in machine language. Therefore, as a sort of intermediate language, there comes the C and the C++ and C#. And humans can definitely communicate with the C's, the C++, the C#, which now is converted to the machine language for the computer to understand. And with that, we have come to an interesting conclusion of Unit 1 of Module 1, CIT392, Computer Laboratory 2. We'll take a break now. You'll be duly communicated when the next class will be. And we will be looking into programming in C. Very interesting stuff there. I'll always encourage my scholars after every unit, and in fact, within the units, if there are exercises, we will be taking them one after the other, making sure we understand what is being asked in the exercises and the assignments, and we already have an understanding of what the solution should look like. So I want to encourage you all, from what we have studied so far in this Unit 1, go through these tutor-marked assignments, the TMA here. They are not things that should look new to you anymore. Get some brief answers, 2, 3, 4 lines maximum. Get them ready for an exam condition and get them with constant practice, have them by heart, such that when you are woken up from sleep, you can produce the answer to any of these questions. And that's how you begin to make gradual, intentional steps towards being scholars. I want to thank you very much again, every one of us, for their attention. And I want to wish you all success in the course of this course this semester. Thank you.